Morning friends, we are going to start the unit 2 of the paper 2 of physics, nuclear detectors. First lesson. Nuclear detector is a device used to detect, track and identify the high energy particles. Those are produced in the nuclear decay, cosmic radiation and the reactions in the particle accelerator. They are also used to measure the momentum, spin charge, etc. of the particle. That may come for the MCQs. It not only detect the presence or absence of the particle but also detect the nature of the particle. To detect the particle, number of detectors are developed and they are broadly classified as detector are of the two type, electrical detector and optical detector. Electrical detector based on the ion collection, whereas the optical detector not based on the ion collection. Then you can see saturation ion collection, multiplication ion collection here, counter based on light emission, counter based on image formation. Then saturation ion collection in gases, ionization chamber in semiconductor, GU, HPG, SIU, and in the multiplication ion, proportional counter, GM counters. Whereas in case of the counter based light emission, scintillation counter, or you can see here the Cherenkov counters. And counter based image formation is the bubble chamber, spark chamber, cloud chamber, and the nuclear emulsion. These are the different detectors that can be used to detect the that particular that used to detect the nuclear radiations, especially that we have seen. Nuclear decay or say cosmic radiation reaction in the particular thing. Then we have to discuss about ionization chamber, proportional counter, and GM counter. Then first of all we will see these all are the gas field detector and its different forms such as ionization, proportional counter, Geiger molar counter that we have to see. Interaction between the particles and the matter. As we know, different types of the particles interact differently with the matter. Their penetration and the processes of the interactions are unique to them. To design a nuclear detector and the interaction between the particle and the matter is an important factor. When monogenetic, monoenergetic collimated beam of the particle passes through the piece of matter, there are two cases happening. A particle may undergo many interaction and losing a small amount of energy at every interaction or get scattered by the small angle. A particle may pass unharmed through the matter or may be removed from a beam in a single catastrophic encounter. This figure particularly shows the two cases. These two cases and figure shows the example of an all possible electron interaction with the matter. Here you can see AB has been shown electron interaction with the matter. Here see here incident gravity beam is incident on the surface at that time. There will be the auger electron, secondary electron, backscattered electron formation. It may give the heat, visible light, or say characteristics, X-rays, or say Bremsstrahlung, or it may diffracted or transmitted electron, refracted electron. Okay, that cases are possible when this particular thing is happening. Okay, this is we are not going in the detailed part of this particular thing. Now gas field detector we will see. Gas field detectors are most widely used detector for the nuclear radiation that may cover the MCQ. Gas field detectors are based on the principle of ionization and excitation caused by the charged particles while passing through a gas. Here the construction is shown. You can see the cathode is there, anode is there. Then the insulator is there, ionization radiation is there, anode is there, gas is there. Okay, then electrical circuit is there. It consists of the cylindrical chamber filled with the gas at a pressure of the amount 1 atmosphere or less. A thin wire is placed along its axis. it well insulated from the walls of the chamber. A voltage V is applied between the cylinder and the central electrode through a resistance R and a capacitor C. The wire electrode being at a positive potential with respect to the conducting cylinder as shown in the figure. When the nuclear radiation enters the chamber, it ionizes the gas present in the chamber, thus creating number of positive ions and the electrons called the ion pairs. The energy deposited by the incident radiation is directly proportional to the number of the ion pairs created. The motion of these ion pairs to their respective electrodes constitutes an ionization current which gives rise to the voltage pulse. The height of this pulse is proportional to the ionization current. The pulse is amplified and passed through the suitable electronic counter. W value when the charged particle interact with either ionization or excitation takes place. In ionization, ion pairs are created. In excitation, no such ion pairs are formed. The energy consumed in excitation process is wasted because during the excitation no electron reaches the anode. The average energy lost by the incident particle is creating one ion pair is called W value. The W value is always greater than the ionization energy of the gas. That may come for the MCQ. The W value is always greater than the ionization energy of the gas. It is a function of the gas present in the detector, type of radiation under detection and its energy. In most of the cases, W lies between the 25 electron volt to 35 electron per ion pair. That may come for the MCQ. The variation of this logarithm of the number of ion pairs formed or pulse height which is across the resistor with applied voltage for a gas field is plotted in the figure. Here the different region has been shown: region 1, region 2, region 3. The name has been given region 5 and region 6, region 5. Region 5 is a Geiger-Müller counter region. Then there is the ionization chamber. The ionization chamber works on the principle that the charged particle passing through matter moves electrons from the atoms. This process is called as ionization. The number of ion pairs formed gives the information about the nature of the incident particle as well as its energy. Ionization chamber are of the following two types: pulse ionization chamber, current ionization chamber. In the pulse ionization chamber, the ionization produced by the charged particle traversing the gas is detected as single voltage pulse. This is known as a non-integrating type. And whereas the current ionization chamber, the voltage pulses are not separated but continuous accumulation of the charge leads to flow of electric current and is known as the integrating type. Then pulse ionization, or you can say the non-integrating type chamber. It consists of the cylindrical conducting chamber with a metallic electrode AB located on the axis. This you can see the pulse ionization chamber. When the charged particle enters the ionization chamber, ionization of gas takes place, resulting in the ion pair formation. Due to the presence of the voltage, positive ions move towards the chamber walls and the negative ions electron move towards the central electrode. Now an extremely short electric flow or pulse passes through the R, which develops a voltage across it and has some charge on the that particular condenser. This pulse is applied. This pulse is amplified and then passed through a suitable counter. Current ionization chamber, or say integrating. This is a non-integrating. The schematic diagram has been shown here. You can see ionization is coming, then AB is electrode. In the it consists of the cylindrical chamber with the two electrodes A and B placed at some distance from each other. A suitable potential is maintained between the two electrodes and a resistance R is also induced between two electrodes. When the charged particles enter the ionization chamber, they produce the ionization of gases and results in ion pair formation. Then you can see here when the charged particles are enter the ionization chamber, they produce the ionization of gas which results ion pair formation. The ion collected by the electrodes due to the potential established between them. Now a very weak and continuous current flows through the resistance R. The current can be measured by the sensitive instrument. The strength of the current is directly proportional to the rate at which the ionization radiation are entering the radiation